say they host a international competition called ImageNet Large Scale Visual Recognition Challenge. Then they use the test data, which comprise over 1 million images to across 1,000 object classes, and use it to measure the performance of algorithms in reconnaissance tasks. So the result was reported here. You can see that that is the error rate of winning algorithms from 2010 to 2015. You can see that the error rate of winning algorithms steadily decreased, and especially in 2012, um, witnessed a significant drop in error rate, and that is the starting point of CNN, convolution neural network. And from 2012 to 2015, all the winning algorithms were CNN. And you can see here in 2015, the error rate outputted by a CNN was just surpassed the ability of a human, like a a PhD student participate in this challenge and do the task same many computers. And the winning model in 2012 is supervision, which is uh, a convolutional neural network, had around 7 or 8 layers. And the next 2 years, the winning network uh, is CNN again, but which was which was deeper, um, which was deeper about 19 layers. Yeah, and the winning model in 2015 is RedNet, which is also a neural network with about over 100 layers. Um, you can see that in 2012, CNN is certainly invented. It's called AlexNet, but actually CNN had been studied since 1998. Um, it was able to it is able for disease classification task, and it just look the raw pixels here and pass it through some layers like convolution, subsampling, or fully connected. But the question here is why CNN became popular several years ago, even it was invented around 90s. So the answer is thanks to Moore's law, we got faster computers with much more transistors. Yeah, and we also have GPU, and we have some large data set like ImageNet and Pascal, thanks to tools like Mechanical Turk. So to talk about the Discord overview, Discord focus on one of the most important problems of visual recognition, which is image classification. The problem relating to image classification, there are many problems relating to image classification, such as object detection, like we draw bounding boxes around the objects and determine what category it is. Or another problem is action classification or image captioning. So furtherly, we need to face tons of challenging problems like semantic segmentation here, or 3D understand, or activity recognition, VR, AR, or another interesting problem, which is image description, like we describing the image as a whole of large graph like this. Like we need to give the information about object identities, object relationship, object attributes, actions, and etc. So that is the end of the first lecture, just the introduction. So anyone have question?
I think now you can continue.
Yeah. So move on to the lecture 2. Is all about image classification. So image classification is a core task in computer vision. Like we assign a single label to a image from a fixed set of categories like that. Like you have a image and you need to give it a label. But it's quite apparently it's quite easy for human to to assign a label to an image, but computer is but for computer it is a hard problem, and the computer see an image is a grid of numbers, like for example an image here has 800 by 600 pixels, and each pixel is represented by 3 numbers, like giving the information about the red, green, and blue hue. And the big challenge that computer should maybe face is the viewport variation, illumination. Here you can see information, background clutter, in-class variation, occlusion. Like this challenge, this problem is when the images have a different matrices of number, but somehow they are still representing the same object, and our models need to be robust to this condition. So many attempts have put in this. So the first approach, they began finding the edges and the corner of the image, and like they said that when the image have the corner like this or like this on these lines, they will be assigned to the cat label. But this approach is not very scalable, because when we want to predict other categories, we need to start over. So another approach is data driven. Like we started with creating a data set of images and labels, and then we use a we use machine learning technique to train a model and then use that model to predict new images. That you can see here, just basically it's just include two main functions. The train function, the output, the input of the train function is images like the training data set and the equivalent labels. And then in the breed function, we use that model we got before, and with the new images and predict label of the new image. And this is the key insight that all these things start working very well over the last 10 or 20 years. So here is the example of training set. Like we have many images which all have its own label here. And the first and the simplest classifier is nearest neighbor. Like it take the test image and started comparing it to every single image of the training set, and then after comparing, they predict the label of the closest training image. Like, and the training function is quite simple. They just try to memorize all data and the label. And at the inference time, they break the label of the new images by compared to average every single training example in the training set and find the most similar training image. Is the general idea behind nearest neighbor. And the data set we use for assignments and for this course is CIFAR 10. And this data set include about 50,000 training images and 10,000 testing images, and across 10 classes here. And when we have the test data here, and we find the closest images of the training set here. And the question is how to compare the images. So the simplest way is to compare images pixel by pixel, and then add up all the differences to a real number. So the first distance metric is L1 distance. When we get the absolute value between this value of test image and training image, and we have a matrix of differences here, and after that we add up all the difference to a real number. And another distance metric is L1 distance. Like we take square root of the sum of square difference. So to visualize the difference between two metrics, you can see that you can see that in this image we have 1, 2, 3, 4, 5 classes, and the region of classes in training dataset. And you can see that the boundary of the classes here is quite straight, like this. But in L1, L2 distance case, you will not see that. And it's one the difference between this is lie in the, you know, I don't have a clear understand about that, but as I understand, L1 distance depends on the coordinate axis we chose. Like in this case, we chose y axis here, x axis here, so the boundary will stick along to this axis. And L2 distance doesn't really care about the axis system somehow relating to the school here, but I didn't understand well about that, and we need to discuss about that. Yeah.
Yeah. And what about the rectangle and the circle in here? Those two images. Yeah, that one and the next one in next to it. So what about that between L1 and L2?
You can see that this is the general images about Manhattan distance and Euclidean distance. Like I think I didn't understand much, but let me think.
Yeah.
I just stuck here, but so I need our discussion about that. Anyone have answer?
So if anyone have answer, you can speak up, or you will leave the question here and answer next time.
Yeah. So.
Okay, we can move on.
Yeah.
I can note my question here.
Yeah. So we just talk about the nearest neighbor, but you know, choosing a label from a list of label is quite doesn't make sense. And we have another approach. It is K nearest neighbors, and instead of copying the label from nearest neighbor, we take majority vote from K closest points. Like from visualization, we can see that with different value of K here, K equal 1, K equal 3, K equal 5, we have different like boundary. So for is in order to understand it, I think we need to see this active demo.
Wait a second. So why there y area in here? In k equals 3 and k equals 5. So their y area, so they didn't belong to any category, right? So why is that?
I will explain here.
Okay.
Let's choose the number of classes is 4. And so for the k hyperparameter, if we choose 3, I find the picture that has outlier 0.
Outlier, you mean the yellow dot, right?
Yeah. Let me see. K equal 1. Here. You can see that when we choose then the k equal 1, here we have like graph boundary like this, and
I think your screen is free right now.
My screen.
Yeah, I still have the same image here.
What?
Okay.
You can see my web page.
No, I'm still in the PowerPoint right now.
Oh, yeah. Okay.
You can end the share screen and share it again.
Yeah.
Okay.
Yeah.
Okay. Now.
Sorry. Yeah, here. When I choose the number of classes 4, and then we need to see with different value of k, we will have different boundaries. And if k equal 1, we can find that the boundary is quite rough here, and it's quite fit to each data point here. And when k equal 4, then let me choose another example. It's quite hard to say, but I will try. I find the image that I can say that I can describe easily.
So we still have blank area.
Okay. The blank here, the white area.
Yeah. Why is that?
Your question is a question in the CS231 and course, and the teacher answered that the white space is the reason that And the reason that if an image in this reason and uh, in this reason, so they don't belong to they doesn't belong to they doesn't belong to any classics. I got the answer, but
it doesn't explain why.
he said that, but I don't really understand. He said that this boy have um, doesn't have any label.
No, it has label, right? It's purple.
No, no, no. The reason determine the class of the boy.
Yeah, but there are one purple dot in the white area, right?
Yeah, I don't understand much, but
Okay, then. Can anyone have answer here? Okay, one more note.
like you can see that when k equal 1, the purple reason fit this point with this kind of boundary. But when k equal 2, is this by the reason exclude this point. um, this if this proof that the when k equal 1, it likely to fit to the outlier like this, and k equal 2, k equal
Can you make
3.
it 3?
I don't understand.
So in k equal 2, maybe there are a point that they have two different categories. So there are two neighbor, right? And two neighbor have different categories, so they can vote. But how about 3? I don't think they are another reason. Not sure.
Me too.
So if it is even number, so there the case that they can vote, right? So that is one reason. But when the k equal 3, they are still the y area. So there must be different reason for that. I'm not sure about it. So we need to research more about it.
Yeah. So
Okay, I
can
know it there, so you can continue about your slide.
okay. So you can see my slides.
Yeah.
Okay. Um, so the question is, you may ask what value of hypermetric k should be chosen, and the answer is we need to try um, different k value and pick out the, 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 the best one that give give the best performance. And the first idea is um, choose a hyperparameter case that work best on the data set. But the fact that KU1 always works perfectly on training data. So we stick to the second idea, like we split the training the data set into the train and the test sub data set, and choose have choose the k value that work best on the test data. But as you know, we shouldn't touch to touch the test data set until the until um, until the final stage of our project because we need the test dataset to evaluate our model performance, you know.
Yeah.
So well, the third idea is split dataset into 3 sub datasets, like they are train dataset, validation, and test. So we are tuning the value of k based on this validation set and test the performance on the test set.
Is that supposed to be same idea as to chain of variation and test on test?
So
this is the same idea, like split it into, right? So you just
what do you mean?
so the idea two is like train and test on the test, and the idea three is train on validation and test on test. It's pretty much the same thing, like you only have two sets to determine which case you want to be.
I didn't catch it. Can you say it again?
So the idea too is like you train on train set and you test it. So maybe you have two data to evaluate the case. And the idea three, you say you train on validation and test on test. It's pretty much the same thing. Like train on one and test on two. It's pretty much the same thing, right?
Oh, no.
What difference?
Like when in the idea two, when you evaluate your model performance on the test data, and then you decide what k value work best. But then when you choose the best case, then you have no test data to test your new value of k. Like then there's no unseen data to evaluate.
And what about the idea three?
So we need to save up the test data until the final state of our project. We need to so we split the train data set here into the training and the validation data, and we train train our models on training data set, and then tuning and tweaking the hyperparameter on the validation. Then it means that when you test on when you test different value of k on validation, and then you choose the right value of k, the right case that have the best the best performance, and then so at the end we at very last minute of our project, like we at that time we use TED to test our overall performance. So, but in the case where the size of our data set might be small, so we have another sophisticated technique for hyperparameter tuning. It is cross validation, like we split training set here into n equal folds. In the example, it is 5 equal folds. So we use n minus 1 folds for training and 1 left for validation. And for it and for each value k, we will iterate over which fold will be the validation fold. Like in this case, we choose fold 5, and then we choose fold 4, fold 3, fold 2, and fold 1. And at the end, we evaluate the performance and accuracy of our model by averaging the performance across this this experiment. Um, so this figure depict the example above. Like we have 5-fold cross validation run on different k value, and then we decide what k give the best performance. You can see the y-axis here is cross validation accuracy, and 5 point here you can see 4 point here is the like in the same line, and 1 point is and 1 point is the accuracy of one way that we chose the validation fold. You can read here. For each value of k, we train on 4 folds here, and evaluate on the fifth. Hence, we receive 5 accuracies on the validation fold, and and we get the average value of of each k, and we draw this trend line. Like this is the average point, and yeah, and you can see that around 7 k equals 7 here give the high gate accuracy. So that is it is the way we chose the right k value in practice.
Yeah, and what about the vertical line, the straight line?
Vertical line, you mean
yeah,
here?
that line.
This line this is called the error bar, like indicate the setup deviation of 5 point here. So in assignment we also need to do the experiment over different k value from 0 to 100 to choose the right k.
So the way you choose the best is the best on the average, right?
Yeah.
Okay.
But in fact, k and n on image never used because um, um, at the test time we need to compare the test image with each of image in training set, so it's very slow. And besides, this metric like L1 or L2 on pixels are not informative. Like you can see here, we have the original pixel and 3 different images here. So the first version is we have like the black boxes cover the eye and the mouth, and we have the the object is moved down to several pixels, and this is tinted image. So, but in fact, when we apply L1 distance, these three images are given the same L2 distance um, with the original image. So we can conclude that L2 distance is not good at capturing this perceptual distance. So why I say it the distance metrics are not informative, are not sufficient.
So you say in the line is like all three images have same L2 distance on the length.
Yeah, this is the original image, and we subtract the subtract the three image here to the.
It's not supposed to be the same, right?
I think it will within the same L2 distance, because you can see that the background here and here is kind of the same as original, and yeah, and
So it's not supposed to be the same. So how about the original one and the thin one? So the first one and the fourth one, I don't think they have similar L2 compared to others.
I did have the same thought with you, but the slides said that. So I think it the reason why they said that is the can these images have the same background, and the percentage of background is quite large. So when they have the same background, then the L1 L2 distance will be the same. I think that.
Yeah, you can say that for the original one and the ship one compared. So the box and the ship, they have very similar background to compare to original. So those two L1 and those two L2 may be the same, maybe not very different, but the thin one is have very different background.
Oh yeah, yeah.
So the L2 of the thin one and original will be different with the ship one and box one be just the original.
Oh,
So they can be the same.
Uh, your comment is also what I'm wondering when study. So I think this is a question we need to discuss later.
Because they're not the same, so this means the L2 distance is not good.
No. They said the distance between three images with the original are the same. They said
Really?
they said that, yeah.
I think they're mistake in here, they're not the same.
Actually, the same question was asked from the lecturer who was delivering this video. So he said he deliberately put the L2 distance same just to put up an example to show that the distance metrics on pixels are not that informative. So these are uh, not proved how they are same, but he said that he somehow made it the L2 distance same just to give an example.
Really?
Yeah, he had
Okay.
explained in the lecture.
Okay, maybe we should reward it sometime.
Yeah.
Okay, you can continue.
So to conclude, I will talk about the advantages and disadvantages of KNN classifier. So you can easily see that this classifier is simple to implement and understand because we need only to store the data, the training data, and then use that to compare with the test images. So it's quite understandable. It's quite easy to understand, right? And
yeah.
And this classifier takes no time to train, since all that is required to store the training data. And so that leads to the one of the disadvantages, like the classifier must remember all the training data and store it for further comparisons with the test data. So that is space inefficient because dataset may easily be gigabytes inside. And this classifier is different from other common classifier, like which use the training dataset to give the final model that summarize all the feature of the training dataset into a weight or something else, and use that weight to in the inference phase, and then they can throw away all the training dataset. But in this case, the KNN, we all need to store all the store all the data. So this is why it is very inefficient.
They call it lazy learning because they don't have model, so they just store data. They don't have model.
Yeah. So another disadvantage is we pay the high computational cost at test time because classifying a test example require a comparison to every single training example. So, but in practice, we need to care about the test time efficiency much more than the efficiency at the training time. And the final disadvantage is like I said before, L1 and L2 distance on raw pixel value is not adequate. Since the distance correlates more strongly with backgrounds and color distributions of images than their semantic content. Like you can see here. Yeah. You can see that the color distribution between the two images is quite the same. So they assign the label of actual the shape to a animal or something like that. So yeah, you can see that it is a disadvantage of KNN.
Yeah, so they most likely just assign the background together. The background most likely stick together.
So we have another powerful classifier, which is linear classifier. Basically, this approach has two major components, like there's score functions and the loss function, and the loss functions will be talked later in the lecture 3. So you can understand the score function is a mapping from the raw data to a class score vector. We all work with the CIFAR 10 datasets. It has 10 classes here. So, for example, this is an image has 32 by 32 by 3 numbers. So when we pass the image into the function f, we will get a 10 dimensional column vectors. That is the score vectors here. So yeah, the f function is just the function that have as like the information of image and the width as and the width are the arguments of the f functions. So it's called the parametric approach. For image classifier, the f function here is just the multiplication between x and w. And you know the output is the vector is 10-dimensional vector, so it is 10 by 1, and x is the first step we need to set out our image into a single row vector, like in single column vector like this, like we 32 times 32 times 3, so we get a single row, a single column. So because of the dimension of output is 10 by 1, and x is 3072 by 1, so the dimension of W matrix is here. So also we need to apply to a bias vector, which indicate the preference of the classifier between each class to other classes. So for example, we suppose that we have a 4-dimensional image like that, and we need to stretch the pixels into column like this, and we multiply them together, multiply W to by the image here, and then plus the bias, and we end up with the score vector like this, the score vector. Yeah. So there is a trick here that we should merge the column of bias vector with the W matrix to maintain easily. Like we need only only parameter here, and it's simply to understand, and in the practice we only need work with a matrix, with only one matrix. Yeah. So there are some way of some way of interpretation the linear classifier. You can understand firstly you can understand the linear classifier as a combination of hyperplane, and in this manner you can interpret each image as a single point in this space. So the entire data set is set of points, and each 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 classifier for each class is aligned here. So it separates the one class to another classes. So you can understand that each line of the W matrix is a director that you know this a row of W is a director for each class. Like when you change the values of this row, then the line this, like I suppose that the first row is the weight of the first row is the weight of car class. So when you change this value, then this line will rotate in different direction, and when you change the bias value here, and then this line will move around. Yes.
Okay.
And if bias is equals 0, then the classifier here will cross the origin. So another way of thinking about linear classifier, it is that you can understand the linear classifier is as template matching, like each like you can as I said, each row of W is a weight of a class. So in this case, you can understand that each row of W is considered as a tablet for one of the classes, like this. That is the template for plain class after training. Like yeah, as the flow of a model, like you train your model and get the final weight, and we and here is a visualization of the first row of the weight. Yeah, and because of we have 10 rows in the weight matrix, so we have get 10 templates here. Each image represent one template for each class.
Can you back a few slides about when they introduce the weight? Here.
Yeah.
So the weight here has 10 rows, and each row has the same size of the image, right?
Same type of image. What do you
Same
mean?
same size of the image.
Yeah. As I said here, the weight have 10 row represent the 10 class, and 3074, 72 here is like the weight for each of pixel in the image.
Okay.
Okay. So at the inference phase, you can compare you only need to compare the test image with each of these template and find the closest one that give the closest label. The closest one that give the smallest distance, then it would be the label of test image. So you can you might have a question like why we use dot product. um, yeah. In the second line, I say that the score of each class for image is then obtained by comparing each template with the image using an inner product one by one to find the one that fits best. But the question is why we use inner product to comparing the each image with the test image. So it lie on the basic mathematical mathematics that when we that the dot product say the similarity. I don't know. The dot product say like the um, like when the dot product is high, then the two vectors point is have the same direction. So that is quite is kind of a measure of similarity. Similarity, yeah. I mean,
So it's
so
like the scale product of two vectors, like the scale of two vectors.
can you say it again?
The dot product can compare the difference between the angle of two vectors.
Yeah.
When you
Yeah.
dot product of two vectors, then you can obtain the similar
Yeah.
angle. I'm not sure.
Yeah. I think it's right. When the dot product is high, it means that the it means that the template is quite similar to the test image, and that would show the label of template to the label of test image. So then, but as you can see that we after training we get a set of templates here, and then um, you know when the linear classifier most some most of the object in the training dataset into a single template, like you can see here, the host template here, that simply it has two heads here, turning on, um, turning to the right and turning to the left. So so you can so this proof that in the training dataset we have the host uh, turning on the right and turning on the left. So you can see that, yeah. And but may you may notice that um, the the car template is quite reddish, like so it seems that the dataset have so many red car. So this is a you know the disadvantage of linear classifier. Like this class the template may be biased based on the training dataset. In other words, that is can generalize to it can generalize to other mode of cars, like the blue car or something different from red. So for foreshadowing, neural network will improve this problem. You can you can understand that a neural network will be able to develop intermediate neurons on its hidden layers that could specify car types like green car facing left, blue car facing front, etc. And the new neurons on the next layers could combine this into a more accurate car score. Yeah. So just for shadowing.
Yeah.
So I think we should talk about the feature scaling in the assignment later. So you have the intuition about the grade, but how to measure the goodness of grade matrix? In this next part, I will talk about two approaches of loss function, which is able to quantify our unhappiness with the score according across the training data. And you know, in order to know how a weight matrix is good or bad, we need to define a loss function, and then we and then we minimize the loss function to get the optimal parameters. So suppose we have a given data set including n and examples here. Like we need to compute the loss function on each of data point, and then we average these losses across each data point. So in the assignment, I need to you know I need to I will talk about it later. For the first approach I said before, as I said before, we have two approaches of loss function, which are SVM and softmax loss function. So for the first one, about the SVM loss function. So you know SVM stand for multi-class, stand for support vector machines. So in this case, we work with 10 classes or more. So we call that multi-class support vector machine. So basically, you can understand that the multi-class support vector machine slot is a accumulated loss function over incorrect classes, like we can see the formula here. So we also need to compute the score vector of each image. Then we got of each image on each data point. So we get the Li here, stand for the loss of the data point I. So the loss will be 0 if the score of the correct, the correct class is greater than is greater than the score of incorrect class followed one certain value. So you can see here SYI is the score of correct class, and the value here is a delta value. It's quite hard to say, but I will try. You can see that you can understand that delta is a design margin or design gap between scores of correct classes versus that of a score of incorrect classes versus that of correct classes. Like you can see in the picture, generally multi-class support vector machine wants the score of incorrect class is to be higher than all other. Oh no, I'm sorry. The multi-class SVM won the score of the correct class was higher than other scores by at least delta. So delta here is the margin between the score of correct class with other classes. So when the when score is at this region, it will cause a certain loss.
Yeah, so basically, it not only one the correct class will be have small score, but it also have one to make the different gap between another.
Yeah.
Just to make sure something like that. So it one greater and also greater than the delta.
Yeah. It means that the differences between score of correct class versus incorrect classes is greater than a certain delta value. So the SVM loss is has another name that is hinge loss. You can see somewhere on the margin loss is also the same meaning. So here's an example. Like we suppose we have three training examples here. Three training examples here, and three class which are cat, par, and frog. So after computing the score, we have this. We have in the score vector of the cat image like this. So it is it is how we are computing the loss value for this image. Like we take the max of 0 and and in this case, cat is the correct class, right? And then we need the score of incorrect classes, which are car is 5/1 and -1 7 -2 the correct score, correct class score, like this. For the first incorrect class, we have this formula, and we continue to accumulate the loss. Accumulate the loss for other incorrect classes like this. And finally, we end up with a single number here. So similarly, we can compute the loss value of the second and the third examples here, and then the overall loss is the advantage value over 3 examples, like we plus like 2.9 plus 0 plus 12.9 and divide by 3. But there is a problem here. If we have a set of parameters W that correctly classify each example, it means that loss is equal 0. And is it W unique? The answer is no, because when we any multiple of these parameters like this, lambda times W, where lambda equal than greater than 1, so it also will it's also give 0. It's also given 0 loss, because this transformation of this uniformly straight all the score magnitudes, and hence also their absolute difference, like you can see here. When we use double weight, like weight twice as large, then we have the last difference here. The last difference here, then we also get the same loss value. Yeah. So in order to make this grid fixed into a certain range, we need to extending the loss function formula with a regularization penalty. So, as we learned in the Coursera course, the regularization term is used to make sure our models be simple, so and make the in order to make our model be simple, so the grid need to small at a certain level, Then we need to include the function of grid here in order to make it small, as well the loss function, the loss value. So there are some common use of regularization term. They are L2, L1, or elastic net. It is L1 plus L2, but the version of regularization we will use in this course and in our assignments is L2. Like we take the square of weight and multiply it by a lambda value. Like lambda value here is the strength of regularization strength. So in order to so we can see that regularization have some advantages, like it penalizes large requests, tend to improve generalization of our model, and it means that no input dimensional can have a very large influence on the score by itself. That it will lead to the overfitting problem. I think you can understand this slide because we we all also learn in the Coursera class. So for let me see. So here is the example. So the differences between the L1 and L2 regularization. I think I should skip this. If you want to know, I will talk about it.
Yeah, you can talk about it.
Oh yeah. You can see that the suppose that we have the input value x here is 1 1 1 1, and we have two weight vectors like w1 and w2. The weight w1 is 1 0 0 0 and w2 is here. We can see that when we multiply x with multiply x by w1 and multiply x by w2, it will give the same values like this. So so yeah, both weight vectors give the same dot product, but the way L1 and L2 penalize our loss function is different. You can see that the loss, yeah, the regularization term here, like we take the square of W, and then L1 penalty, the W1 weight is 1, like you square 1 plus 0 square plus 0 square here, and we got the result 0. And while the L2 penalize the weight 2 is only 0.5, like we take the square of each element here and we get the 0.5 here. So as you can see that the weight the penalty here is less than here. So in other words, that L2 regularization prefer W2 more. And the reason is that the distribution of weight here is more diffuse and more smaller, so it prefers this more than we just focus on the first pixel or something, the first value of input. So yeah, but we can ask how to choose the value of hyperparameter lambda. So the answer is make we will choose the best lambda based on cross validation method, and it will be solved on my assignment. And another question, how to choose the value of delta. And do we have to cross validate it? In fact, it turns out that this hyperparameter delta can safely be set that equal to 1 in all cases. But it depends on how large the weight we have. Like when the weight we have, the weight when the weight is large, then we get the differences. When the weight is large, then we have the distance between this is large, so we need to a larger delta. Yeah. So in our assignment, we always use the delta value is 1, because we all use the regularization, so it will penalize the magnitude of our weight. So we always use delta equal 1.
Yeah. Nice, teacher.
Yeah. So another approach I said is I would like to say about is SOMARK classifier. Another name is multinomial logistic regression. It's another way to understand the score vector after computing after the multiplication. Yeah, you can see here there is a transformation of the score here when S is the score. So we pass it into a transformation to get a normalized log probabilities of the classes. This transformation is called the SOMARK function, and then we got new score. A new score. Then we will compute the loss function according to this kind of new score. So the optimization problem here is maximization maximization of log likelihood. Like you take the log of the probability above and minus here. The log function is a increasing function, so we always want the probability of correct class is high as much as possible. So we need overall the probability here is large, and the log is increasing function. So we want this is log. So the loss function is minus log. So we want to minimize. I hope you understand.
Yeah.
So here the example of computation, like we take we exponentiate the score here, and we get this new new score I said before. Oh no. After we after exponentiating, we normalize it by this, yeah, with this. So we have a like the distribution here, and we compute the loss function for each classes for each class.
A class or only this class?
For each example, sorry, for each example.
So
Oh,
this example is class cat, right? So it only calculate log for class cat. So I see only calculate the log for 0.3.
you know, we get this the result here is based on 1 over the result here. Like we take the summarization here, the sum here. So after we get the probability of the correct class of correct class, you know, like this. I mean the input class is a cat, and the correct class is cat here, and we need maximize the probability of the correct class here, and we need to log to minus log of 0.13 here.
Yeah, minimize that.
Yeah. Minimize this is the maximize the
Yeah.
maximizing the probability of correct class. Yeah. So here's a short comparison between the SVM and SoftMax, and you can see with the H loss of SVM, we only take directly the scores here and compute the loss beyond a margin here. But the SoftMax is quite more complex, so we need to go through some intermediate transformation, and then we compute the loss here. But in general, you can understand that SVM sorry. The common flow of loss function computation is we transfer the we pass the grade and the input data into a function in order to get the score value, the score vector, and you know, we compute the data loss, and then we add up the regularization term to the grade to the loss. So it is the full loss of these classifiers. And the first part is the average value over the training datasets, and this is the vector. I also made the detailed difference a detailed comparison between SVM versus softmax in my notes, so I will upload this note for you to read more meticulously. Yeah. So when we have the loss function and and how to determine the parameters that give the best loss value, or in other words, how do we find the best weight? So this is the optimization problem. So there are two main strategies. So the first strategy is random source, like we generate random weight, like we iterate generating random weight, and then when we have weight, we compute the loss function, and the current loss, and if the current loss is less than the best loss, then we will take the best weight is the current weight. But it seems to be like naive.
Not efficient.
That's quite naive. Yeah. But then we move to the second strategy. It is following the slope. Like you can imagine that we are on a hill and we want to get to the bottom of the hill. Then we need to find the slope of the hill and follow to it to reach the bottom. So in mathematics, we have the same intuition, like that. It is gradient or deviation. So the first way to know the slope of a function is called numerically with finite differences. And I hope you can understand this. Like we take we move a point of h to a distance of h and compute the differences between two points and divide to the train of x, and then we get the slope of function fx, right? It's quite abstract, but I hope you understand. So I will. Find a picture that depicts this concept.
Okay. I think this is very strong definition of gradient.
Yeah.
I can't put it.
So you can see. So here is the value of x function when of the fx function when I don't know. Here's the value of fx function when x at when here, and we move to a h station like here, and we got a new value of f function. Then we compute the difference here between the years, like you can see that, and divide to the difference here. That that will give you the slope of function at x at x. I hope you understand what I said. So it is the underlying idea behind the numerical with finite differences. So in one dimension, the derivation of a function is here, but in multiple dimensions, the gradient is the vector of partial derivatives along each dimension. So, and if we starting compute the gradient of a large function in this way, we need to plus a new distance here into each element of weight matrix, and then compute the gradient here. But the downside of this approach is that it approximate. Since we have to pick a small value of h here, while true gradient is defined as a limit as h goes to 0, and it means this is a approximated value, so it will give you a approximated gradient value. Besides, this way of computation is quite expensive. Like, you know, for each element of it of W, you need to compute this function. Yeah, so it's quite expensive to compute. So and then have another way of computing gradient is totally based on calculus. Like we study calculus before that it allows us to derive a direct formula for the gradient, like, and this formula is quite exact and fast to compute. Like you can see the loss function of SVM classifier here, and we have a corresponding formula for gradient here, and and we just apply this formula in computation the gradient of loss function. But it has its own advantages, but there is a disadvantage, which is the way of calculus is so complex here, so it's quite error prone when you implement it because of complexity. So you will likely to have some errors while implementing. So in practice, in practice, it is very common to compute the analytic gradient in this way and compare the result we got to the numerical numerical gradient to check the correctness of our implementation. This additional step is called gradient checking, and I will show you this step in my assignment.
How you compute gradient from the Ly, right? So
yeah,
from the first loss, and how to compute the gradient to the line that you make it either.
You mean why do I have this formula?
Yeah.
It's quite easily. Like this function is a function. This function have two arguments, like WYI and WJ. WYI is the grade from correct class, and WJ for incorrect class. So the gradient with respect to WYI here is it is argument, so we have xi here. So so the max is have value of have two kind of values. It is 0 or a positive number, and when the the loss is equal 0 when this function is less than 0.
Okay.
Yeah. Then the gradient will be 0 as well. But if but when this formula is positive, then you will get the xi here, and minus here and minus here. Yeah. So it's quite easily. It is just to check the formula is greater than 0 or not.
Yeah.
And this as well, in the same manner. So yeah. So when we get the gradient of h weight, then we need to update make an iteration to update the grade into the optimal grade value, and we have the gradient descent algorithm, which iteratively compute the gradient and performs a parameter update in a loop. Like here, it is a loop. Then you get integrate the gradient of weight based on numerical gradient or something like that. To get grade here, so we need to update it by subject to a value of a multiplication between the step size and the quest gradient here. I found it quite quite hard to describe it. I think you guys are familiar to the gradient descent, so I think I will. I don't need to talk about it more. But you know, in practice, the training set have millions of examples, so it seems wasteful to compute the full, the full loss functions over entire tuning set to get the average value, and in order to update just a single parameter, it is the weight. So in practice, we are likely to use mini batch gradient descent more. It is quite easy to understand this concept. Um, um, all you need to do is splitting the training set into different different batches of smaller size than the original training data. And why mini-batch gradient descent makes sense? It is because the examples in the training data are correlated. So the gradient from a mini batch is a good approximation of gradient of the full objective. You know, when the when we split the training data set into batches in a random manner, so you get a random set of examples. So I think it makes sense when we use a subset of examples into updating the weight. So the size of mini batch is usually 32, 64, and 188. We use Power tool in practice because many vectorization operation implementation work faster when their input are sized in powers of 2. So that is why we have this number. The extreme case of this is the mini batch contains only a single example. So this is called stochastic gradient descent. But in yeah, I hope you're familiar with this definition. Like here, the first line, when we sample 256 examples from the training data set, and we compute the loss function of these examples and compute the gradient, then update the weight according to this. And in practice, sampling data batch in the random manner, so it makes sure the nature of our data. So that's all for the first 3 lectures. So Does anyone have a question? Hi.
Okay, so anyone have questions to Hằng? So please speak up. So no one has question and everyone understand, right?
So next
Yeah.
part
It's
should
Yeah,
basically, yeah. So I'll ask after maybe on Monday, because in theory it is like quite understandable, but while implementing I was facing some issues. So I'll let you know regarding that.
Yeah, maybe it's related to assignment, right?
What?
Your question is related to the assignment, right?
Yeah.
So Hằng,
Yeah.
did you did the assignment or not?
Yeah, I did.
So maybe you can also read down here.
Yeah, sure. Can you see my web page?
Yeah.
Yeah.
So yeah. First, I need to connect to my Drive. There are 3 main assignments I need to complete relating to the first 3 lectures. So the first one is KNN.
Yeah, actually, I am also trying to. So I was chasing some, but right now my there's issue something with my laptop, so I'm not able to share right now. So that's why I'm telling that maybe later I'll text and maybe what the issue I'm facing.
Okay.
What's your issues?
She's not able to share right now, so maybe later.
Yeah.
Oh,
Later.
yeah. Okay. Sure. Wait for me a minute to review the code. Yeah. So the KNN is the KNN assignment has like it has 2 stages. The first one is computing the distance, like the L2 distance, and in order to compute the distance between test image and training datasets, we have some way of computing. So the first way is the easiest way to compute the distance is that we use the 2 loops over the test the test test and the training. You know, in practice we not only pass a single image. Instead, we pass a set of images as a test data, and we need to iterate over it. And then in order to compare each image with each image in a training dataset, we need to make a nested loop here to compute the distance here. And there's another way that much that's faster is compute the distance using only one loop over the number over the test data, like this. And the fastest way of computing the distance is we use no loop, no iteration over training set, no iteration over test set, like this. And the difficulty here is in order to compute the distance with no loops, it's quite abstract, and we need to have a deep. We need to using our brain more to compute while no loop is needed.
And yeah, can we do the assignments like on our next meeting?
Yeah, okay.
Okay.
Yeah, some of it was to be presented by Bhavas too.
Okay, so
Yeah.
you need time to prepare for that. Yeah, I think it's okay. It's already 2-hour meeting, and I think everyone is tired right now. So
Yeah.
maybe we will do it next week and start with Hằng doing the assignment, and then Prihat, you will start present your part. So yeah. So overall, it's really nice presentation from Hằng, and thank you. So it's really well prepared, and yeah, it's really easy to understand. So yeah, well done. So I think we will end the meeting here.
Yeah.
And will Pablo be coming to the meeting?
Pablo, I think he will be busy with the project right now. So because of the deadline he facing right now, so it's quite urgent. So I will report to him later. But yeah, overall it's quite okay meeting right now.
Yeah.
Can you also tell him about our internship letters?
Can you say it again?
Can you also tell him about our internship letters?
The letter about internship, right?
Yeah.
Yeah. The
I think I
appointment
will talk
letters.
to Pablo and Nam. I'm not sure because I'm not familiar with the work right now. So I will try my best to alert the guys. So yeah. So I already see you guys start Nam few time in the intern group. I'm not sure how it's going. So you guys haven't received the letter yet, right?
Yeah.
No.
Yeah.
Okay, then I will talk.
No.
Yeah, so I think we can end the meeting here, and I will do my best to talk to
Okay.
Nam and yeah.
Okay.
Thank you.
Thank you.
Okay, have a
Thank you
nice
for
day.
listening.
Yeah.
Yeah.
Well done. Bye.
Bye.
Bye.